In the last video, what we talked about was the free energy of mixing, but if you remember, the only thing that we talked about was the entropic component. So what we actually did last time was we talked about what are called ideal mixtures. And these are mixtures where the energy is basically the same between the mixed and the unmixed state. Or what I said last time is that there are no preferential interactions between the different particles. So an A particle interacts with another A particle with the same strength that a B particle would interact with a B particle, or that an A particle would interact with a B particle. So all of the interaction strengths are the same. So in that case, there's no real net effect in terms of the energetics when you mix something or leave it demixed. On the other hand, we saw that entropy does change when you mix things together. And we came up with an expression that we can write it two ways. We can either write the free energy or we could write the entropy. So if I was to write the entropy of mixing, then we calculated or we derived that this was equal to Boltzmann's constant times the volume fraction of the A component divided by the degree of polymerization of the A component multiplied by the natural logarithm of that volume fraction. And then we just had the other component. So we had plus 1 minus phi A, because the sum of the volume fractions must be equal to 1. And that was divided by the degree of polymerization of the second component, and then multiplied by the natural logarithm of its volume fraction. So the next thing that we did was looked at the free energy of mixing. In fact, I think I missed a minus sign, didn't I? There's a minus sign out front. The next thing we did was look at the free energy of mixing. And if you look at the Helmholtz free energy, the free energy of mixing, and I should also say before I do this, this is per particle. So this is actually delta S mixed divided by little n, and that's the total number of particles. So delta F mix divided by n is the same thing as delta F mix with that little bar on top. And all we do is just multiply this by T, because this would be delta U of mixing minus T delta S of mixing. And we'll put bars on top of those. And again, if we have an ideal mixture, then this delta U is going to be 0. Again, because there's no difference in the interactions between the different species. So that's how we arrived at the fact that the free energy of mixing for an ideal mixture was equal to kBT, and then times all of that stuff in the brackets. So phi A divided by NA, log of phi A, plus 1 minus phi A over NB, log of 1 minus phi A, please fit. Yes. Right? Okay, so that's the expression that we're starting with today. And again, this is only if the interactions are the same. So just based on this equation alone, we can come up with a couple of different scenarios that might happen. So we could have what are called regular solutions. And I'm missing a term, but that's the term we'll get to today. But a regular solution is what you would study in physical chemistry, in like a chemistry department towards the end of the semester or the end of the first semester. A regular solution is going to be a mixture of small molecules. So mixing water with ethanol. So in that case, for a regular solution, these degrees of polymerization are both going to be 1. And in the absence of preferential interactions, you can see that just based on the free energy of mixing that we have here, these are expected to always mix together. And in the case of water and ethanol, that's certainly true. But in the case of water and oleic acid, not true. Olive oil, right? So something's clearly missing, but we'll get to that. So there's regular solutions. The other things that we can have a polymer solution. So if I took polynipam or polyethylene glycol and dissolve that in water, then I would have a polymer that's dissolved in a small molecule solvent. So we can have a polymer solution. Polymer solutions are one of my favorite things to measure and look into. So in that case, it doesn't matter which N we call which, right? So let's just say that Na would be the polymer, and that would be whatever the degree of polymerization is of that polymer. And then the other one, the small molecule component, would have Nb is equal to 1. So that will be a polymer solution. And then the last thing that we need is what happens if we mix two polymers together. That would be a polymer blend. So we'll call polymer blends mixtures of two different polymers. Polymer blend. I don't know how to say this. We'll just say that you have Na much bigger than 1 and Nb will be much bigger than 1. So those are the three cases that we have. So again, if you were to take this in a physical chemistry class in a chemistry department where you're not going to talk about polymers at first, then you would get to something that's called regular solution theory. And what regular solution theory is you're going to have the entropic part described by an ideal mixture. So entropic, or I'll just say entropy is due to an ideal mixture. So you assume that mixing is ideal, but you also assume that there are interactions. And so there are also interactions. And the interactions are going to be captured by some kind of term. In the textbook that I happen to own, when we talk about mixing different elements, so to form an alloy. So imagine that you're going to combine, I don't know, lead and tin together. I think that's pewter. I don't recall exactly. I think it's pewter. So you can combine those two metals together, and that will form an alloy. And so the interactions in that case will be described by this parameter called omega. But that's quickly going to be problematic for us because when talking about entropy, we use omega to talk about the number of microstates. So I just mentioned that in passing. So we're going to not do that today, but we're going to characterize our interactions by something that we call chi. And chi, sometimes we'll put AB as a subscript, and that chi AB is going to be what we call the Flory-Huggins parameter. Not only that, sometimes we call it different things. We might also call it the interaction parameter. And if you think back to when we were talking about light scattering and even neutron scattering, the interactions between the different species in the solution were characterized by the second virial coefficient. So chi AB is related, it's not equal to, but it's related to the second virial coefficient. So all of these things that you learned are still true, and we're just going to explore them in a little bit more detail today. Okay, so we've done entropy. How do we consider interactions? What is the energy of binary mixing? Let's go back to our lattice model, because again, the ideal mixing was constructed on a lattice. So let's construct similarly the energetics, so the differences in the internal energy or the enthalpy, depending on which free energy you're using. Let's construct that on a lattice. So first thing is, let's look at the different particle types that we have. So I'm going to draw these particles. These will be A particles. I think last time maybe A was blue. I don't care. It's fine. Don't worry about it. All right, and here's these ones. These will be B particles today. And so just based on this, how many different interaction types are there going to be? A with A, B with B, and A with B. So there's 3 different types of interactions. So you could, let me copy this. Maybe. Copy. Paste. And let's paste one more. Okay, so when we talk about AA interactions, then clearly that's going to be an interaction of this type. And there's going to be a certain strength associated with it, and we're going to call that little u AA. That's the strength of the interaction, or the amount of energy that's associated with this interaction. So I'll just call it the strength of interaction between A and A. And what I can also do is I can plot it schematically, because in general, these interactions will take a certain shape. So if this is R and this is U of R, then as you saw in the homework, a common way of describing this interaction would be with something like a Leonard-Jones potential. And the shape of that Leonard-Jones potential will look something like this. You'll have an attraction and then repulsion as distances get very short due to overlap of the electron clouds. So this distance then, in other words, the depth of this well in the potential, is what UAA is. And you can also see from this that UAA is going to be less than 0. So that's an important thing to keep in mind, because after we go through this, we're going to come back and try to connect this theoretical description with something that hopefully we could measure experimentally. And as you might guess, chi is something that you can measure experimentally with a bunch of different techniques, one of them being neutron scattering. Okay. So that's the AA interaction. And then similarly, we'll have an interaction between B and B. I haven't quite figured out how to get this to be flawless, where every time I want to copy and paste an image, it just works. But I digress once again. Okay, so I've got two B particles here. Whatever, I'm going to move this just because you're going to get these notes, so I want them to be kind of neat. So anyway, here's an interaction between two B particles. And as you guess, the interaction strength will denote UBB. And it will also be the strength of interaction between two B particles. And the shape of that interaction would look the same as it does with UAA in general. And it's going to have a different strength. So the depth of the well will be different, meaning that interactions between like species can have a different strength, or between two B particles, I should say, will have, or can have, a different strength than two A particles. So you'll get UBB still that is not necessarily equal to UAA. And because of the shape of the potential between these two things, UBB will also be less than 0. And then that leaves the final case where I've got, let's see, let me copy these particles once more. So I've got that particle, and then I've got that particle. And so it's just the same thing. There's going to be an interaction if these things are close enough, and there will be a UAB term. So those are the only interactions that are possible in my system. And so now the question is, what is the difference in those interactions between when the system is mixed versus when the system is unmixed? And this is where it gets a little problematic in the theory, because we're doing this on a lattice. And the way that we do this, we're going to look at the average values of these interactions based on average how many neighbors the particles are going to have with each other. And that's going to be problematic. And it'll be problematic for this reason. If I draw my lattice, and let me not draw too many boxes. Let's just say I have 9 spaces in my lattice. So I'm going to look on average how many particles around a given particle. So to be a little clearer, let's say that here is one of my A particles, then I want to get an idea of what the interactions are with that particle and all of its neighbors. Well, if I do that, I'm going to have an interaction here, 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 and here in 2 dimensions. So there's going to be a coordination number, which is equal to 4 in 2D. And that's going to be how many neighbors this particle is going to have on average. And then in addition to how many neighbors there are, you can see that I could have either a red particle, I could have a red particle in all of these boxes actually, or I could have a blue particle in these boxes. So I'm going to have to figure out a way to see what is going to be in those neighboring sites. So that's problematic. This is where the theory is a little, I don't want to say sketchy, but it's a caveat that you have to keep in mind, because we're going to ignore the fact that there are correlations between where one particle is and where the other particle is. If we were just doing a mixture of small molecules, if we were looking at a regular solution, then this wouldn't be a problem, what I've drawn here. But if I have a polymer, so maybe I'll just label this. If this was a regular solution, everything that I'm talking about is fine. The problem is that if I was doing, let's just say I was looking at a polymer solution, then I still have this lattice. But the issue is that there are correlations between the particles. So if I have an A particle here, there's going to have to be an A particle in one of the adjacent sites, because all of the A monomers are covalently bound to each other. So I'm going to have some correlations like this. And so the particles that are in adjacent sites are not necessarily independent. There's going to be some correlations. So this would be the case of a polymer solution or a blend. And there are correlations between the particles. There are correlations in the species or the chemical identity of each lattice site. So we will ignore those correlations. And those correlations are due to covalent bonds between monomers. So we will ignore those. The other thing that we're going to do is we don't know exactly what the species is going to be. So we're going to have to consider this on a statistical basis to see on average what we expect would occur. So in that case, what we end up doing is what we call a mean field approximation. We look at what the average should be. So on average, what are the neighbors of a particular particle going to look like? So those are the caveats. Those are the underlying assumptions in what we're about to do. Okay, so that's where we are. Now let's think about what this might look like. Let's look at a single particle first. So we'll look at a single particle. And by that, I mean a single lattice site. Okay, so let's look at what the average interaction energy is going to be for one lattice site. Well, we're going to have, let's just call this UA. And what's that going to be? Well, these interaction strengths that I drew up here, this UAA, UBB, UAB, these things, in fact, I'll just say this, and this, and this, these are all pairwise. Okay, so they're between two particles. So down here, this is going to be the average interaction that a single particle is going to see because of pairwise interactions with a certain lattice site. So this is, let me write it down. This is going to be UAA. so the strength of an AA pairwise interaction, multiplied by the volume fraction of A, and then plus UAB multiplied by the volume fraction of B. So this is on average what you would expect for the interaction between one lattice site and another lattice site. So if I was to put this in words, this is the average interaction energy between two lattice sites in the mixed state. All right, so let me draw a picture of what this kind of represents. So I'm going to draw another lattice. This UA is going to be something like this. It's going to be the average interaction energy of a certain particle here with, for example, another lattice site here. Because that other lattice site could be an A lattice site, in which case the strength of that interaction would be UAA, but it could also be a B lattice site, in which case the interaction energy would be UBB. So on average, it's going to be this weighted sum that has the volume fractions to take into account the fact that there's going to be a certain distribution of those species around each lattice site. Okay, so this, let me circle this so that we'll remember where it is. We're going to come back to this. We can do the same thing with B. So we could write down the way I've drawn it here. Did I get my colors mixed up? No, I didn't. Okay. So the way I've drawn it here, this is going to be UA. But if that particle was a B particle, let me even just draw it on the same lattice, then I'm going to look at what the average interaction energy will be between a B particle and another lattice site. And that will be given by capital U, B. Well, that's going to be similar, that expression will be similar to what we had for UA. So this average interaction energy will be the strength of a BB interaction multiplied by the volume fraction of B, so multiplied by 1 minus phi A. And then there is the potential that I could have a cross term. Just wanted to make sure I had the same notation. So there's the potential of a cross term, which would be UAB, and then multiplied by the volume fraction of A. So that would be on average how many A particles are around that B particle. Okay, so I've got that. That's for a single site. Now I have to look at how many of these things I'm going to have overall. So I have to sum up all of the A particles and their interaction energies. So what I'm doing next is I have to sum up UA for all A sites, and I have to sum up UB for all B sites, and that will be the average internal energy, or the average energy of my system in the mixed state. So this will be, let's call this U of the mixed state. And we have to have the number of particles. So let's say that for every lattice site, how many neighbors are there? Ooh, let's see. Let's draw it in 2 dimensions first. How many neighbors am I going to have in 2 dimensions? Remember these equations. So this equation for UB and this equation for UA, that's the interaction between one lattice site and one neighbor. So that's only 2 particles. If you look at the lattice, in 2 dimensions, you have 4 what we call nearest neighbors. So if I draw that down here in 2 dimensions, if this is my lattice site, then I have 1 neighbor there, 1 neighbor there, 1 neighbor there, and 1 neighbor there. So this would be z equals 4 for the coordination number. There are 4 nearest neighbors in 2 dimensions. What about in 3 dimensions? In 3D, here's my lattice site. I have a nearest neighbor up here, nearest neighbor down there, nearest neighbor right there, nearest neighbor right there. Well, it looks like the 2-dimensional case. And then I have 1 forward and 1 behind me. So I have 1 right here and 1 right there. So you can think of this in coordinates. This is maybe the x coordinate and this is the y coordinate. So this is the x coordinate, y coordinate, and z coordinate. So in 3 dimensions on a square lattice like this, the nearest neighbors are 6. Those are just kind of limiting cases. So this means, though, that if I want to look at the total energy, then for each lattice site that I have z neighbors. Now, how many total lattice sites do I have? I have little n total lattice sites. So little n total lattice sites multiplied by, I need the number of A particles because this is the interaction energy for an A lattice site. How many do I have? Well, little n times the volume fraction will give me the number of A lattice sites. So this will be multiplied by phi A. And then I have to sum up the B lattice site. So I have UB, the interaction energy for one B lattice site with another lattice site. And then how many B sites do I have? Well, I've got the total number of lattice sites multiplied by the volume fraction of the B particles. That will give me the number of B lattice sites. So this will be multiplied by phi B, which is going to be the same thing as 1 minus phi A. And now there's a problem. So we're going to have to fix this a little bit, because if I look at my lattice, I can just do it here even. If I have a certain lattice site, let's consider the lattice site in the middle, I'm going to have an interaction with that lattice site. But when I look at the other lattice site later on in my sum, I'm also going to have that kind of interaction, just by the nature of how I'm counting. Same thing here. I'm going to have the central lattice site interacting with that neighbor, but as I'm counting, I also count that one. In other words, the expression that I've written so far is double counting the number of interactions. So I have to divide this by 2, and that will get rid of the double counting. Kind of like when we were calculating the Debye form factor in neutron scattering, we had to get rid of the fact that we were double counting when we switched the limits of that integral. So this is where I'm starting for getting the interaction energy for my system in the mixed state. But what I want to do is I want to substitute in for that and simplify things a little bit so I can just get a nicer expression, because I still have to look at the unmixed state. So with this in mind, let's take this down here. Let's substitute in for UA and let's substitute in for UB, and the expressions are going to get a little lengthy, but we're going to be able to simplify them pretty easily also. So U in the mixed state is going to be the coordination number times the number of lattice sites divided by 2. Then we need to substitute in for UAA. Or sorry, UA, capital UA. So this is going to be UAA phi A plus UAB 1 minus phi A times phi A. So to remind you, this term here is capital UA. And then we just need to do the same thing with UB. So I'll write it on the next line to save us some space. This will be UBB times 1 minus phi A, and then then added to UAB volume fraction of A, and then multiplied by the volume fraction of B. And again, just to remind you, this part here is UB. And I think it's clear, but this is the same thing as phi B. Okay, so let's look at what we've got here. We have phi A times phi A and UAA. So if I start to write down these terms, I've got coordination number, total number of lattice sites divided by 2. And then I've got UAA times phi A squared. And then going back, I've got UAB times 1 minus phi A times phi A. So I'll get plus UAB phi A 1 minus phi A. So that takes care of the first term. And we'll just do the same thing with the second term. We'll expand that term with UBB. So we're going to get plus, let's look at this term first. Let's look at this. We've got UAB times phi A times 1 minus phi A. So it's actually the same term that we just got. So we've got UAB phi A 1 minus phi A. And then one last term, which you can see, brown, let's pick brown. UBB times 1 minus phi A times 1 minus phi A. So one last term, UBB 1 minus phi A squared. And that is the energy in the mixed state. Or that is the energy if the system was mixed. So this is going to be an important result for us. Okay, well now what? Well, now we need to look at what the energy is in the unmixed state. So going back to the lattice, let me draw it with an even number of lattice sites just to make it clearer. So let's draw 16, I guess. So if I was to look in the unmixed state, I would get something like this. It would look almost exactly like the system I drew when we were discussing the entropy of mixing. So this in the unmixed state is going to look something like this. I'm going to have a bunch of A particles that are completely segregated from all of the B particles in the system. So all the B particles will be down here. Okay, so if I look at a certain A lattice site, then what's its interaction going to be with its neighbors? Well, it's going to see another A site here, another A site here, etc. So for the A particles, if we look at the energy of the unmixed state, well, we're going to have the number of total lattice sites times the coordination number divided by 2 to eliminate double counting. And then what? Well, we're going to have, what's the only interaction strength? The only interaction strength that's possible in the A state is UAA, because they're demixed from each other and there are no B neighbors. So UAB is not going to come into our equations because there are no B particles that the A particles will interact with. So this will be multiplied by UAA, and then we need the total number of A sites in the lattice. So this will be multiplied by phi A. And then if we want the B particles, then we'll have UBB multiplied by phi B. And that will give me the interaction energy in the unmixed state. Now, if you've been following along carefully, you're going to like freak out right now. You're like, but wait, you forgot all of these particles here, because those A particles will interact with the B particles. You're not wrong, but if you consider a very, very large system, the surface to volume ratio is going to be very small. In other words, the bulk terms, the terms where A particles are surrounded by A particles, are going to outweigh those interfacial terms. The interface is going to be negligible. So that's why we don't consider these effects. We neglect surfaces or edges. Okay, so I realize we're neglecting that, but it's not going to be important when you're looking at a very large system. All right, so this is going to get a little messy now, because what are we after? Well, the big picture here is we're looking at delta F of mixing, and that's going to be delta U of mixing minus T delta S of mixing. We already have the delta S term, but we don't have the delta U term, so we're going to have to get that. And this term will be the energy of the mixed state minus the energy of the unmixed state, just like we did with the entropy. But actually, the expressions that we were doing the other day were a lot simpler if we looked at the intensive quantity. In other words, if we normalize by the number of lattice sites, it's a much more convenient measure to look at because it doesn't depend on the system size. So you can see that if we do that, if we divide through by n, that term is going to go away. So I'm going to come back to that, but just keep in mind that the energy of the mixed and the unmixed states that I've written right now are extensive properties. The free energy that I'm after is going to be an intensive property. So I'm going to have to divide at the end of all of this. So just remember that. Okay, so we just have to write this down, and it's going to have a lot of terms, and we're going to have to start simplifying them and expanding them and things like that. But just bear with me, because it's important, because we're going to get a value, or we're going to get not a value, but an expression at the end that's kind of convenient for mapping what this Flory-Huggins parameter means, or what the value of the Flory-Huggins parameter is versus what it actually means. So delta U of mixing will be the energy of the mixed state minus the energy of the unmixed state. And we'll just do this. So we're going to get, I'm going to write it over here, Zn divided by 2. I'm going to look at my notes here so that I make sure I get every single term. I'll have UAA phi A squared plus 2 UAB phi A 1 minus phi A plus UBB phi B squared. This is the time where I miss teaching this in person, because if I make a mistake, somebody always says, hey, you forgot a minus sign, or you forgot a term. I think I got this though. All right, so that's the mixed state, and we'll subtract from that. I'll put it in a different color. The unmixed state, which is UAA times phi A minus UBB times phi B. So just to be clear one last time, this is not a good way to do it. This term is U mixed. And this term is U unmixed. Okay, so let's start grouping some things together. So rewriting, we'll have the coordination number of lattice sites divided by 2. UAA multiplied by phi A squared minus phi A. And then what? Plus 2 UAB phi A 1 minus phi A. That's not going to change. And then plus UBB multiplied by, this is going to get really messy, 1 minus phi A squared, and then minus 1 minus phi A. Whew. Okay, so we're just going to expand this and simplify still. So I'll write it in a different color. This term here, if you expand the binomial and combine terms, you're going to get 1 minus 2 phi A plus phi A squared minus 1 plus phi A. So you can see that some terms will cancel. That term will cancel with that one. This term will combine with that term, and what you're going to get for this whole thing is phi A squared minus phi A, I think. Yeah. Okay. So believe it or not, we're almost there. This term phi A squared minus phi A can be written as, if you just factor out the phi A times 1 minus phi A. So each term, if you notice, has that. We've got phi A times 1 minus phi A times 1 minus phi A, and then phi A minus 1, or phi A times 1 minus phi A. So each of those terms has that. So let's factor one more time. We've got coordination number of lattice sites divided by 2, times UAA plus 2 UAB plus UBB multiplied and now we get to the first mistake. I'm missing a minus sign. Every single time. Bane of my existence. Okay, so if I factor out phi A from this term, I get phi A times phi A minus 1. And down here, I'm going to get the same thing, phi A times phi A minus 1. And notice that this term is phi A times 1 minus phi A. So one of them has an opposite sign. This is why you don't skip steps. So this is Zn divided by 2 times UAA phi A times phi A minus 1 plus 2 UAB phi A 1 minus phi A, and then plus UBB phi A minus 1. I got so excited about this energy of mixing that I skipped a step and I missed a minus sign. I almost broke physics. All right, so now you see that I've got phi A times phi A minus 1, phi A times phi minus 1, and phi A times 1 minus phi A. So if I multiply minus 1 by phi A minus 1, then what I'll get is minus phi A 1 minus phi A. So now I can factor everything out. So what I get for my energy, or the difference in my energy of mixing, delta U mixing, will be coordination number of lattice sites divided by 2, times, we'll put this term first since it has a positive sign. So that term will come first. So we'll get 2 UAB, and then making the substitution that we did right here, we're going to get minus UAA minus UBB. And all of that stuff is going to be multiplied by phi A times 1 minus phi A. Okay, so that's going to be the change in my energy for my system if I mix it. So let's do some things. Let's look at what the free energy of mixing would be then. Delta F mix per lattice site will be delta F mix with the bar on top. And if I divide by n, again, I'm just going to get rid of that term in the prefactor. So what I'll get is Z divided by 2, 2 UAB minus UAA minus UBB multiplied by phi A 1 minus phi A. So again, this term is delta U mix with a bar on top per lattice site. And now let's add on T delta S to this. So this will be plus KBT phi A divided by NA log of phi A plus 1 minus phi A divided by NB log of 1 minus phi A. And that is my complete free energy of mixing, taking interactions into account, or taking preferential interactions into account. So that's fine. That's a great expression, but I can do a couple more things to it. One is that I can take that interaction term inside of the brackets with the entropic term. So if you notice, all I have to do is take into account the fact that this has got KBT out front. So if I want, I can divide that interaction term by kBt and take it inside of those brackets. And so what I get is an expression that's a little closer to the one that we use regularly, which is the change in free energy upon mixing is kBt times phi A divided by Na log of phi A plus phi B divided by Nb log of phi B, and then plus that change in energy upon mixing. So plus Z divided by 2 divided by kBt, and that's because we took it inside of the brackets. And then in the numerator, we've got 2UAB minus UAA minus UBB. And then this whole thing is multiplied by phi A times 1 minus phi A. And now everything is inside of those brackets. So that is fine. I'm going to do one more thing, though, because I don't necessarily know all of these interaction strengths. If I'm doing a computer simulation, I might, but if I'm measuring this experimentally, I'm probably not going to know all of these interaction strengths. But I can characterize the behavior of my system with respect to the interactions by a single parameter. And I can do that by grouping all of these terms into a single coefficient that I call chi AB. And so this is the quantity that I was referring to at the beginning of the video. And this is the quantity that we refer to as the Flory-Huggins parameter. We also will call it something like maybe the interaction parameter. Or if you end up using it a lot and you end up saying this a lot, you kind of get tired of saying that all the time. And a lot of us just call it chi, with the understanding that chi is the interaction parameter between the species. So this chi then, we will define as Z divided by 2 kBt, and then times 2 UAB minus UAA minus UBB. And I can also write it a different way. I can split up that 2 UAB into two different terms. And I could also write this in a different way that allows you to see maybe the connection between what I'm talking about here and what I was referring to in the previous video when I was saying that there's no preferential interactions between the species if I'm only considering the entropic component. So I can also write this Flory-Huggins parameter as Z divided by 2 kBt, and then multiplied by UAB minus UAA plus UAB minus UBB. So when I write it this way, maybe it's clearer to see that what this Flory-Huggins parameter is telling us is the difference in the strengths between having the particles isolated by themselves and having them in contact with each other. Having them in contact with each other is going to give you that difference. So what is the difference between UAB when they're together and UAA if they were just by themselves and segregated from each other? So maybe now you can see what I mean, because for these terms, if there are no preferential interactions, then again, everybody has the same interaction strength. And if everybody has the same interaction strength, then UAB would be equal to UAA. And similarly, UAB would be equal to UBB. And what is it? The transitive property tells me that that means that UAA is equal to UBB. So if that was the case, then there would be no preferential interactions. And you can see that chi would be equal to 0. And if chi is equal to 0, then you can see that this whole entropic term, this whole enthalpic or interaction term would completely go away. So that's what we did last time. And so when we have those interactions, you can see the difference here. So with that said, the full expression that I have for the free energy of mixing per lattice site, which again is delta F mix with the bar on top, that is equal to KBT phi A divided by NA log of phi A plus phi B divided by NB log of phi B, and then plus chi times phi A 1 minus phi A. And that's the form that we're used to. So this is what we call the Flory-Huggins equation. And of course, it's subject to a number of assumptions. We derive this using a lattice model. We're neglecting the fact that there are edge effects and interfaces. We're assuming that those are negligible compared to the bulk terms. And you can also see that it's composed of two terms. You have here the entropic term, as well as the energetic term. And this equation gives rise to or predicts some complicated behaviors that we will discuss in the next video. And if you think about it, last time we saw that the entropic term is always less than or equal to 0 because of the form that it has, which means that the entropy always increases, right? Because the entropy will be the minus of that. So the entropic term by itself will always be positive, but the entropic contribution to the free energy will always be 0 or less than 0. So it'll always promote mixing. The energetic term, whether it promotes or doesn't promote mixing, is going to depend on what its sign is. And if it's 0, then it's just an ideal mixture. And so the system will behave as the ideal mixture relationships predict. So it's easiest to see some of this stuff if we plot it. So I'm going to plot it in a second using Wolfram alpha. The last thing that I would say about this is how it relates to polymers specifically. So polymer solutions to some extent, regular solutions, yes, it's important, but to a lesser degree than it is with polymer blends. So if we have polymers, if we're not talking about a regular solution, then delta F mixing is KBT. I'm just going to write the whole Flory-Huggins equation one last time. After 20 odd years of writing this, you get pretty good at it. I have this memorized. It's a pretty important equation too. So that's the Flory-Huggins equation. If you have polymers, polymers have large degrees of polymerization. So this term will approach 0 for polymers. And so if that's the case, you can see that this term is the major contribution to delta F of mixing. This means that interactions are everything when it comes to mixing polymers together. Entropy doesn't help you much in terms of mixing. Interactions are going to dictate whether something mixes or whether it doesn't. So if there is even a slight unfavorable interaction between opposite species, between A and B, then you're going to demix. Those things aren't going to want to be together at all. It doesn't take much for this to happen. So this is why most polymers tend to not mix, because there's no entropy of mixing, essentially, because it scales as 1 over the molecular weight. Any slight unfavorable interaction, or if another way of saying that is if the polymers like themselves only a little bit more than they like each other, then that's it. They're not going to want to mix together. And we're going to have to think of other strategies to get them to mix together. On the other hand, if the opposite species like each other just a little bit more than they like themselves, then you're going to get really nice mixing between the polymer components. So that's, again, easiest to see if I plot this. And so I'm going to plot this in Wolfram alpha to give you an idea of what this kind of looks like. So the last thing to do is to look at what these functions are, to look at what the free energy of mixing looks like if you were to plot it. And the reason is this will give you some information about what's going on. So you can see some of my old inputs down here, but I'm going to go to Wolfram Alpha like I am here and show you how to plot this. So let's plot the free energy of mixing. Let's divide through by kBt. So all we're interested in is what's in the brackets, not the kBt up front. So that will give us the general shape. kBt is just going to scale it depending on temperature, right? So this is going to look like, let's let x be the volume fraction. So this will be x times the log of x plus 1 minus x times the log of 1 minus x plus, I realize this term is kind of useless, but let's let chi be 0. 0 times x times 1 minus x. And if x is the volume fraction, then that means that x runs from 0 to 1. So we'll say for x from 0 to 1. And you kind of already saw what the curve is going to look like. So what I've plotted here, I've set NA and NB equal to 1. So this is a regular solution. And because chi is equal to 0, this is an ideal mixture. So here is the free energy of mixing divided by kBt. And you see that it's always negative throughout the range, throughout all of the possible volume fractions of A. So the sign of this doesn't really matter. I know you're used to thinking of the free energy being less than or equal to 0 for something being favorable, and it being greater than 0 for things being unfavorable. But with mixing multiple components like this, it's a little bit more complex, and we'll see that in the next video. But for this system, this does mix because of the shape of this curve. And so you can see that the function is always less than 0, and it looks like this parabola, and so this will always mix. Now pay attention to the scale here. So the scale, this is about 0.6 minus 0.69 at the minimum of the function. Watch what happens if I divide by the degree of polymerization. Let's say that instead of looking at a regular solution, I'm going to look at a polymer solution. So Na will be really large. Let's say it's got a degree of polymerization of about 1,000. And the degree of polymerization of the solvent will still be 1. And let's just say that everything's ideal. So let's get rid of the chi parameter and see what the entropic contribution to the free energy looks like. So this might take a second. And there it is. So you notice the minimum of the function has shifted to higher volume fractions, and we'll discuss the implication of that. But the overall shape is still the same, and you can see that in addition to the shape of the curve being skewed to higher volume fractions, you can also see that the function, instead of taking a value of minus 0.6869 at its minimum, you can see that now we're looking at minus 0.3 something. So the free energy difference between the mixed and the unmixed states has decreased relative to the regular solution because now we've got a big degree of polymerization for the polymer. We could also look at a blend. So let's set NB also equal to 1,000. And we'll see what that does to the value of the free energy of mixing. So it's symmetric again, but look at the value now. At the minimum of the function, the value is minus 0.00069. So it's practically 0 just by having two polymers together. So this is what I was saying last time. The entropy of mixing scales as 1 over the molecular weight. And so you can see for this symmetric blend of polymers, they both have the same molecular weight, that the contribution to mixing just due to entropy isn't very big. And it doesn't take much to, let's just say we increase the degree of polymerization by a factor of 10. And this is certainly possible with really high molecular weight polymers. You see I've decreased it even more. So I'm quickly approaching 0. So entropy doesn't really help me mix polymers. Let's go back to this case. Actually, very quickly, let's see what happens if we have an asymmetric blend. So you see that the degree of polymerization of B is 1,000. The degree of polymerization of A is 10,000. And still the chi parameter is equal to 0. And so we can see what this looks like. It'll be skewed. So when your molecular weights are different, it'll skew the graph. And you see, once again, it's skewed to higher volume fractions. And if you were to set this equal to 1,000 and instead have a larger molecular weight for B, then it'll skew it the other way. So you can see now it's been skewed to lower volume fractions, and the value is still what it is. And so that's how that works. Let's see what happens if we start increasing the value of the chi parameter. if we set it to minus 1/2 for the symmetric blend, what do you think you'll see? Well, you see that it's negative and that the value at the minimum has decreased now from minus 0.6 something, or actually it was minus 0.0006 something. Now it's negative and quite big. It's minus 0.12, whatever our units are going to be. So you see that that negative chi parameter has made this even more favorable for mixing because it's lowered the free energy of the mixture even more, and we've maintained the shape. And I'll talk about the implications of the shape of this curve in the next video again. So if I made this even more negative, then you can imagine that I'm going to take a negative value of the function and make it even more negative. And that will happen here. You see that now I'm even more negative than what I was at before. So a negative chi parameter means that interactions between opposite species, between A and B, that those are more favorable than interactions between species of the same type, so A or B. If I make this positive, then what this means is that the interaction parameter is such that that opposite interactions, so between A and B, are less favorable than interactions between particles of the same type. So if I was to make this 0.2, it probably won't have a big effect. I was wrong because I have something else in there. So you see that now the free energy of mixing is positive for all values across this composition range. So mixing's not going to happen in this case. You see just a small interaction parameter has led to a free energy of mixing that's always positive. So these polymers will never mix together. And it's just because the entropy isn't helping them mix. So I could decrease the molecular weight of my polymer and approach the regular solution limit. So let's go down to a degree of polymerization of 100 and see what this looks like. Still positive. Let's go down to a degree of polymerization of 10 and see what this looks like. Negative. So you see that the degree of polymerization, as you make your chains bigger and bigger and bigger, this curve goes from being negative to being positive. So in this instance, the particles will likely mix together. And the ones that I just showed you for the larger molecular weights, where you have degrees of polymerization of 100 or more, you see that the curve is positive for all values. So let me go back to this case. Instead of increasing the degree of polymerization, watch what happens if I start increasing the value of the chi parameter from 0.2 to 0.25 maybe. I'm just kind of picking values. You see the shape of the curve that we have here. We get this kind of W-shaped curve where we have two minima, one maximum across the volume fraction range. So this shape of curve is going to have serious implications on whether or not polymers mix together. And I will say that for this system, sometimes they will mix together and sometimes they won't. And that's where this is a little bit different than what you've done before, because notice that all of these values are negative for the free energy of mixing. Even though the free energy of mixing is negative, the shape of this curve is going to lead to situations where the polymers will not want to mix together and they will phase separate. So there's a lot going on here, and that's why we really have to do a deep dive and analyze what we expect to happen. So for now, if you see that this kind of shape for the curve, there's going to be regions that are unstable and regions that are stable. And so our next task is to do a stability analysis to see what we expect to happen. Notice that a chi parameter of 0.3 is leading to this shape, which I said is causing instabilities in our system. Compare that to the case of the regular solution if I get rid of these degrees of polymerization. If I do that, then for the same interaction strength, I still have this U-shaped curve, which is going to be indicative of a system that mixes. And you can see that it's going to take much larger values of the chi parameter to get to a situation where I start to see demixing. And so here's a value of the chi parameter of 2, and you see that the system is still probably going to mix together, but it doesn't take very much above 2 to get to the point where I start to develop this U shape and I start to have regions of instability. So in the next video, what we'll talk about is where those regions of instability are, what's going to happen to our system at equilibrium and how we might think about blending these polymers together even though they don't like each other.